Hello and welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Louis Esperet from CNRS at Grenoble, and he will tell us about universal graphs and planarity.
Okay, thank you very much for the invitation, Anton. It's a pleasure. Yeah, I'm going to talk about two ways for a graph to be universal. And this is joint work with Vida Dujmovic, Cyril Gavoille, Joret, Micek, and Pat Morin. So the first notion that I'm going to talk about is the notion of induced universal graphs. So we said that a graph G is induced universal for some class F, which will always be assumed to be finite in my talk, if G contains all the graphs of F as induced subgraphs. So it's a very natural notion. Maybe the first remark is that G exists because you can take all the graphs of F, you can take the disjoint union of all the graphs of F, and clearly what you get is a graph that is induced universal for the family because all of them are induced subgraphs of this graph. But that's a bit, that's fairly large in general. And what people really want to do is make this graph as compact as possible. So people usually want to minimize the number of vertices of the induced universal graph. Okay, so maybe let's start with a very simple example. Let F be the class of all trees on n-vertices. And I claim that there's a very simple induced universal graph for this class. It's the n-dimensional cube. And you can see that quite easily by induction by removing a leaf in your tree. So now it's an n-1 vertex tree. You embed this n-1 vertex tree in the n-1 dimensional hypercube. This is the C4 on the left. And now there's a perfect matching between the two copies of the n-1 dimensional hypercube. So you can always find an image for the leaf in this graph. Okay, so this proves very easily by induction that the n-dimensional hypercube contains all n-vertex trees as induced subgraphs. And this graph has 2 to the n vertices. But the natural question is, can you do better than that? So the graph has a very simple description, but it might be much larger than the most efficient induced universal graphs. So one very nice tool to be able to improve the bound is a notion called adjacency labeling schemes. So given a class F, an adjacency labeling scheme is some function that takes 2 bit strings in input and outputs either 0 or 1, with the property that any graph G in your class, for any graph G in your class, you can find labels for each of the vertices, and these labels have to be distinct, such that whenever A reads the label of U and the label of V, A is able to decide only by looking at these 2 labels whether there is an edge between U and V in G. Okay, so any graph G in the class, in any such graph, you can label each of the vertices with distinct labels. And when our function A reads the label of U and the label of V for any U and V, it is able to decide whether U and V are adjacent in G or not. Okay? So you can decide adjacencies only by looking at the labels of U and V. So, okay, again, it's not very difficult to show that this always exists because you could give numbers to all the vertices, 1 up to n, and the label of U could be the set of names, the set of vertices, the set of neighbors of U, the list of all neighbors of U. And the label of V, the list of all neighbors of V. And if you look at the 2 lists, you just look whether one is contained in the other. If U is in the list of V and V is in the list of U, this is something that you can check. So an adjacency labeling scheme always exists, but again, what you want is to find a small one. So you want to minimize the number of bits in each label. We say that we have an adjacency labeling scheme with labels of size f of n if for any n-vertex graph in my class and any vertex v, the number of bits in the label of v is at most f of n. Let's see an example, classical example. Let's take f to be the class of all interval graphs on n-vertices. So recall that an interval graph, each vertex corresponds to some interval, and two vertices are adjacent if and only if the intervals intersect. So now what's the natural label that you can assign to each vertex? Well, it's the first thing to observe is that you can always assume that the endpoints of the intervals are integers between 1 and 2n. And now you can associate to each vertex v the endpoints of the interval associated to v. So this takes log of 2n plus log of 2n, so it's 2 log n plus 2. And now if you know each interval, it's easy to tell if two vertices are adjacent or not. You just look whether the intervals intersect. Okay, so it's fairly compact. I mean, 2 log n, it's nice. And well, natural question is, what's the connection with induced universal graphs? Well, the connection, it was observed by Cannon, Naur, Rudich in 1988. The very nice observation is that f has an adjacency labeling scheme with labels of size f of n, if and only if there is an induced universal graph with at most 2 to the f of n vertices for the class of n-vertex graphs of f. Okay, so adjacency labeling schemes are completely equivalent to induced universal graphs. They're just a translation from f to 2 to the f. And let me just explain you why. I mean, the connection is actually very simple. If you have an adjacency labeling scheme A, the labels have size at most f of n, so there are only 2 to the f of n possible labels. And these 2 to the f of n possible labels will be the vertices of your induced universal graph. And when is there an edge between two possible vertices? Well, you look at what the function a tells you about these two, the corresponding labels. If this is 1, you put an edge in your induced universal graph. If this is 0, you don't put an edge. And now it's almost a definition that this is an induced universal graph. And in the other direction, if you have an induced universal graph with at most 2 to the f of n vertices, you can label the vertices between 1 and 2 to the f of n. So this takes only f of n bits for each vertex. And the definition of an induced universal graph is that for any graph G, it appears as an induced subgraph. And you look at what the image is of this graph G. The image is in the induced universal graph, and the image of each vertex will be its label, basically. So the two things are completely equivalent.
Just a quick question to clarify. Do we here, since we're saying that there are 2 to the f of n possible labels, does it mean that we assume that the labels have lengths exactly f of n? Because it says at most f of n in the definition.
So at most, yeah, this is at most, always at most, yeah. This is the definition that I said, labels of size f of n is a shorthand for at most f of n. Yeah.
Mm-hmm. So then I guess there wouldn't be exactly 2 to the f of n. It would be something like, there are 2 to the f of n things of length exactly f of n, right?
Yeah. So exactly. So that will be okay.
This would be like 2 to the f of n plus 1, so roughly. Right?
Yes.
Okay.
Yeah, exactly. So there will be a small, probably some lower order term in the translation if this is not precisely. Yeah, exactly.
Thanks.
So okay, so the two things are completely equivalent, but somehow it's much easier to work with adjacency labeling schemes than induced universal graphs. And we're going to see this with an example. Remember, we had this very simple hypercube that contains all n-vertex trees, but now we're going to make something extremely more efficient with using this idea of adjacency labeling schemes. And the new way is to build an adjacency labeling scheme for n-vertex trees. And the idea is the following. So we give names to all the vertices. So there are n vertices, so the names are between 1 and n. So each one can be assigned some log n bit identifier, just an integer between 1 and n. We take a root, and now each vertex only stores its name and the name of its parent, if it's not the root. So your name takes log n bit, the name of your parent takes log n bit, so it's a total of 2 log n bits. And now, I mean, it's clear that you can decode the adjacencies, because in the tree, the only way that u and v can be adjacent is if it's u is the parent of v, or v is the parent of u. And you can read that in the labels. So it's an adjacency labeling scheme with at most 2 log n bits per vertex. And using the translation that we have just seen, this means that trees, n-vertex trees, they have an induced universal graph with at most 2 to the 2 log n, which is n square vertices. That's much more efficient than 2 to the n. And the scheme is extremely simple. And so there has been a lot of improvements on this n square bound over the years. And the best known bound is obtained by Alpes, Dalgaard, and Knudsen in 2017. So they proved that there is an induced universal graph with O of n vertices. And in terms of adjacency labeling schemes, it means that there is an adjacency labeling scheme with labels of size log n plus a constant. And this is highly non-trivial. So this was about trees, and like most of my talk will be on a larger family, which is quite interesting, which is planar graphs. And for planar graphs, the story starts actually in Georgia. Georgia Tech. It's John Mueller in his PhD thesis in 1988. So he was a PhD student at Georgia Tech. So he observed that planar graphs, there are 5 degenerates. So this means that there is an order on the vertices such that each vertex has at most 5 neighbors preceding it in the order. And you can use this to do exactly the same thing as what we did for trees in the previous slide. You can do that to make a 6 log n bit adjacency labeling scheme. So you store your name and you store the name of the at most 5 neighbors that precede you in the order. And you can clearly check adjacency using this. So this makes 6 log n. So this makes an n to the 6 induced universal graph. So shortly after that, Kanan, Naur, and Rudich, they observed that you can do a bit better. You can go down to 4 log n. And for this, you can use the fact that planar graphs have arboricity 3. So they have a partition of their edge set in 3 forests. And each forest, you can orient it with out degree at most 1. So the whole planar graph can be oriented with out degree at most 3. And what you're going to do is store your name and the name of your at most 3 out neighbors. And again, you can check adjacencies with that. So there's something slightly more subtle that you can do with this arboricity 3 thing. So you have a partition into 3 forests of the edge set between 3 forests. Something else that you can do is go back to this scheme of Alstrup, Dalgaard, and Knudsen that works for forests also, and you can do this scheme for each of the 3 forests and store your label in each of the 3 schemes. So each scheme takes log n bits. So in total, it would make log n plus log n plus log n 3 log n bits. So it's a small improvement. More recently, Gavoille and Labourel, they observed that we can use the fact that planar graphs have a partition of the edge set into 2 graphs of bounded tree widths. So I'm not going to need the tree widths heavily in the talk, so I'm not going to define it precisely, just saying that it's a nice graph invariant that tells you how far you are from being a tree. One tree width 1 are trees and forests, and the smaller the tree width, the closer you are from being a tree. And yeah, so you can partition the edge set of planar graphs into 2 outer planar graphs, so they have tree widths at most 2. And again, you can do the same trick. So the scheme for trees, you can make make it a trim for tree width, a scheme for tree widths that will work with only log n plus some lower order term bits, and you store your label in the two schemes, so it makes a 2 log n bit adjacency labeling scheme. And the interesting thing with this technique is that actually you can prove using Robertson-Seymour graph minor structure theorem that for any proper minor closed class, graphs can be partitioned into two graphs of bounded tree widths. So any proper minor closed class actually satisfies this bound here, 2 log n. And there have been no further progress on this problem until last year, when Marc Bonamy, Cyril Gavoille, and I think it's Michal Pilipchuk obtained a 4/3 log n bit labeling scheme using a fairly recent structure theorem for planar graphs that I'm going to talk in a minute. So yeah, 4/3 log n, so it means n to the 4/3 for an induced universal graph. So what is this very nice recent structure theorem? For this, I need to define what the strong product of two graphs is. So A strong product B. So the definition is written here, but it's easier to see and to understand with a picture. So A is this graph that we really think of as being horizontal, and B is this graph that we think of being vertical. So, and the product of the two, well, each row of this graph is the horizontal graph, and each column of the graph is the vertical graph. So here the vertical graph is the path. And also you need to add the other edges. And whenever you have a horizontal edge and a vertical edge, you have the two corresponding crossing edges. Okay, so this is the strong product. And in all my talk, the vertical graph will be a path, which means that all edges will be either inside rows or between consecutive rows. So what was proved by Vida, Dujmovic, Joret, Piotr Micek, Pat Morin, Thorsten Uckert, and David Wood last year is that any planar graph G can be seen as a subgraph of some strong product H times P for some graph H of bounded tree widths and some path P. So for any G, there is an edge of tree width at most 8, such that G is actually a subgraph of H times P. So yeah, like this, it might not seem very impressive, but the fact that we really have the same graph at each row, the same graph H, is extremely powerful. And using this theorem, a lot of important, fairly old conjectures and open problems have been solved in the past 2 years. So this group of authors, they proved that planar graphs have bounded Q number, which was a fairly old question. And we proved also that the planar graphs have bounded non-repetitive chromatic number, which was also an old conjecture. And in each of these applications, it is really extremely important that all rows are really the same graph. You know this graph in advance somehow. So how can we use this very nice theorem, which I think will have a certain number of other nice applications in the future. So I think it's important to have seen this theorem. So how can we use this to design an efficient adjacency labeling schemes for planar graphs? So what we proved with Vida, Cyril, Gwenaël, Pat, and Piotr is that we can use this theorem to give an optimal adjacency labeling schemes with log n plus little of log n bits per vertex, optimal up to the lower order term. And this gives a nearly linear induced universal graphs for all planar graphs. And so I'm only going to give a very brief sketch of the proof. And actually, I'm going to restrict to the case where H, the graph of bounded tree, which is also a pass. So we are going, in the proof, it will be easier, but also the proof contains most of the ideas. It will be easier to only consider n-vertex subgraphs of the grid with all diagonals. So P, a pass, times a pass, where times is the strong product. It's just a grid with all diagonals. And finding an adjacency labeling schemes for n-vertex subgraphs of the grid is already an interesting problem. Most of the ideas of the whole proof are in this specific case. Okay, so what could be the natural ID? Well, so we have a grid, so we can number the columns from 1 to m and the rows from 1 to h. And the natural ID would be to give as labels to each of the vertices the coordinates. So the vertical coordinate and the horizontal coordinate. But there are two issues with that. And the first issue is that only knowing the coordinates is not enough to be able to say whether there is an edge in G. I mean, if you know the coordinates, you know if there is an edge in the grid. But G is just a subgraph of the grid. So here you have this edge in the grid, but it's not there in G. So how can you give more information to be able to say, okay, this edge is in the grid, but it's not in G? One simple way to do that is to assign to each vertex 8 bits that tell whether each of these possible edges is there in the graph G. And clearly you only need the 8 bits in this case. So each vertex, you can give it the 2 coordinates plus these 8 bits. And now you can really check adjacencies easily. So the first issue is not really an issue. It's an issue of subgraphs versus induced subgraph. The second problem, which is much more serious, is how many bits have we used? Well, we have stored the vertical and horizontal coordinates. So vertical coordinates, you need log m bits. Horizontal coordinates, you need log m bits. And vertical coordinates, you need log h bits. But the only thing you can really say is that m and h are at most n, because you don't know how your graph is. But the only thing you know that probably, yeah, m will not be larger than n, because otherwise some row would be useless. And same for columns. So how many bits have we used? Well, log n plus some small constant. So it's 2 log n. But 2 log n is much more than what we can afford. We want just log n, not 2 log n. So clearly we need to avoid storing the 2 coordinates. Okay. But now,
sorry, may I ask a quick question?
Sure.
It's probably a silly question. I'm just confused. Can't we always embed a planar graph into a sufficiently large grid even without diagonal edges?
No. So here the degree is bounded, so you won't be able to embed any planar graph in this grid.
Okay. I see what the problem is. Thank you.
And I guess that you mean you can embed any subdivision of a planar graph in, yeah, not exactly. You will have the problem of degrees also, but you can embed in the sense that vertices are sent to points of the grid, but you cannot say that you will follow exactly the edges.
Yeah.
But yeah, again, this very specific case of subgraphs of the grid is already quite difficult and non-trivial. Yeah. Okay. So what we have
I guess that what I was thinking is that every planar graph is a minor of.
Yes.
Yeah. Okay.
Yeah. Clearly not every. I mean, not only planar graph. You contain arbitrary large minors. Complete minors. I mean, in this here, yeah, because you can make crossings in this case,
right?
So. Yeah. So what we have really used in the proof is not exactly, I mean, okay, if you have the coordinates, you can really check adjacencies. But the only thing we really need to be able to check adjacencies in this case is to know that two vertices are consecutive on the path, vertical path or horizontal path or like this. We only need to really to query for consecutiveness in a sense. And for this, it's not clear that it's optimal to just give the coordinates themselves to check for, just to check for coordinates to be consecutive or not. So clearly, there should be a way to check that two things are consecutive, that I and I plus 1 are consecutive without storing I completely, but just something a bit more efficient. And this is what we're going to do. And the right tool for the right tool, one very efficient tool to do that are binary search trees. So the idea will be to store, so here is one of the horizontal paths with numbers between 1 and 15. And the black vertices here are the vertices of G. So G only contains a certain number of these vertices. These vertices are in black. And what we're going to do is construct a binary search tree whose nodes are precisely the coordinates of the vertices of G on this path. So let me recall what the binary search tree is. A binary search tree, it's a binary tree, so it's rooted. The root is always at the top, whose nodes are integers, and that has the binary search tree property. And this property is that for any node, all the left subtree has labels that are less than its label, and all the right subtree have labels that are more than this label. And if this is true for all nodes, then this is a binary search tree. And this is a very practical property for searching whether some number is in some list, for instance. Also, you can it supports insertion. You can insert new values at the leaves. You can also delete values, and it's it's very nice data structure, very nice and simple data structure. And yeah, so maybe let's So why is it interesting to use a binary search tree? How can we use this binary search tree to design labels? So the coordinates are the nodes. How can we, with that, build some labels for our scheme? Well, the idea is that the label will be the position of each coordinate in the tree. So, and to define the position, whenever you start at the root, whenever you go left, this is a 0. Whenever you go right, this is a 1. So for instance, the label of 12 will be 1, 0, 0. The label of 1 will be 0, 0, 0. Okay, so each vertex here will record its position in this binary search tree in this way. And it's a binary tree, so if you don't have too many labels, the depth can be log of the number of labels if this is completely balanced. So the labels that we're going to use are quite small, just log of the number of possible labels. So let's make a quick computation. Assuming that G is well distributed among the rows, there are h rows. So G has roughly n over h vertices per row. So if we do this, so this binary search tree will have n over h vertices. So if we can take some binary search tree that is completely balanced, the depth will be roughly log of n over h. So this will be the size of the label of the vertices of the horizontal coordinate, and then we can store the vertical coordinate as before. So this is 1, 2, 3, or up to h. So this costs log h bits. So we've been using log of n over h plus log of h. It's log n bits. So we're not going for 2 log n. We're not going for log n. And this seems to be correct. So this is a lot of assumption, but we can make computation work even if this is not exactly like this. So we are good on the size of the labels. So the labels will be the positions of the coordinates in a binary search tree. Now we need to check what I said, that what we were interested in is whether two labels are consecutive. So how can we check whether 3 and 4 are consecutive in the binary search tree? Well, in binary search trees, when you have two consecutive numbers, say I and I plus 1, they have to be in a very special position. If you have I and I plus 1 in your binary search tree, then one of them must be here, and the other must be the rightmost leaf in the left subtree. Or one of them is there, and the other is the leftmost leaf in the right subtree. This is the only possibility. So here you look at, for instance, 8 is the leftmost leaf in the rightmost leaf in the left subtree of 9. Or 15 is the leftmost leaf in the right subtree of 14. Okay, so if you have I and I plus 1 in a binary search tree, their relative position is very restricted. And in particular, if the depth of the tree is small, there are only a handful of possibilities of where this one can be relative to this one, or vice versa. So what you can do is give a small advice or small code to each vertex in the tree. Okay, so yeah. All right, so when when you are I and I plus 1 in a binary search tree, they have to be in a very specific way, and you can always tell the position of one with respect to the other with a small advice, which would be the difference of the levels between the two. And if you live in a binary search in a tree with depth at most d, or here it would be at most log n, then writing this difference is extremely cheap. It's log n. So we can always afford giving this small advice to each of the vertices, telling 8, for instance, your I plus 1, which is 9, but it lives just 2 levels above you in this way. Or telling 15, or sorry, 13, your 14 is 1 level above you in this way. We can give this advice to each of the vertices because it's very cheap. And yeah, we have to remember that 8 here, I mean, since its label will just be its position in the tree, 8 doesn't know that it's 8. It only knows some position. But it knows that its I plus 1 should be at some position in the tree. So, okay, using its position and its small transition code, it can know where I plus 1 is. And this is exactly what we need to make this consecutiveness work. I mean, now having this code, you can really check for adjacencies. You just look at your position, use your transition code to know where where your I plus 1 would be. And when, as the decoder, you just look at the I and look whether the other one is I plus 1 or vice versa. So you can really use the fact that being consecutive in a binary search tree is extremely specific to check for adjacencies. So everything works as planned. We instead of storing exactly the coordinates, we just store some positions in a binary search tree plus some additional information, and we are able to do as before, checking whether two things are consecutive. So everything works as planned, except that we have a problem, which is that in the previous scheme where we had the vertical coordinates and the horizontal coordinates, 4 in a row knew that it was also 4 in the next row. I mean, 4 knew that it was 4, and 4 knew that it was 4. But now people don't know their name. They don't know anything about their name. They only know their position in a binary search tree. So for instance, there's really no possibility for this vertex 4 to know that, I mean, that they both know that they are the same number. I mean, for the moment, we don't have anything, we don't have any mechanism that would ensure that these two vertices somehow know that they are the same vertex, that they have the same coordinate. Because we're not storing the coordinate, we're only storing a position. And there's no real way that, I mean, if we don't pay attention, the binary search tree for the first row might be very different from the binary search tree of the second row, because even the coordinates that will be stored in the two binary search trees, they will be different. And this is a big problem. But we can be a bit careful and make sure that two consecutive binary search trees are not too different. How can we do that? Well, when you jump from one row to the other row, some new vertices appear. Maybe this vertex appear. And as I told, inserting new keys in a binary search tree, you can always do that at the leaves. But if you insert a new node at the leaf, you don't touch anything. So you don't change the position of the vertices. So this is good. Like when we will insert new vertices, it won't change the positions of the other vertices. So this is good. And also some nodes are deleted. So 3 is deleted. And deleting a node in a binary search tree, you delete it, and all the subtree moves up. And when moving up is the same when you look at the position, the same as taking a prefix. If you go up, you just consider a prefix. And again, knowing which prefix it will be, you can store that with a very small transition code again. And it will be small because you cannot, you just need to store how many levels you go up. So exactly in the same way we stored some transition codes to know where I+1 was, we are going to store a transition code that tells you from your position in one binary search tree, what will be your position in the next binary search tree. And you only need a very small code to do that. So this is what we do. We start with the binary search tree, and we update our binary search tree each time. And each time we update the binary search tree, we add some small transition code to say, okay, in the next binary search tree, the binary search tree of the next layer, here is what your position will be relative to your actual position. So this works very well, except that when we add things at the leaves and we remove things, the binary search tree that was balanced at the beginning is not balanced anymore. And this is a problem because to be able to say that this is log of n over h, we really have to have something that is completely balanced. And removing things and adding things arbitrarily at the leaves, it's pretty clear that things won't be balanced anymore. So we have a rebalancing operation, and this one is much harder to do without breaking the complete structure of the binary search tree. So the core of the difficulty of the proof is to make sure we can rebalance the tree little by little at each step without breaking the structure. But otherwise, most of the ideas of the proof are in what I told you. So yeah, so this is the proof. So now I'm going to, if there are no questions, I'm going to talk about another notion of being universal. So in this notion, we wanted to contain all graphs in a class as induced subgraph. And in the next notion, which is called just being universal instead of induced universal, what we want is that our universal graph contains all the graph of f as subgraph simply. But now, like the right measure, the right thing that you want to minimize is not necessarily the number of vertices, because a complete graph on n vertices contains all graphs on n vertices as subgraphs. So minimizing the number of vertices wouldn't be very interesting. So instead, what we want is to minimize the number of edges. Okay, so like we know that if we consider all n-vertex graph in some family, we will always have a universal graph with at most n square over 2 edges, one of the complete graph. And we want to do better than that. For planar graphs, so there's this very nice construction of Gavoille, Chung, Erdős, Graham, and Spencer from 1982. And they used separators to prove that planar graphs have a universal graph. N-vertex planar graphs have a universal graph with n to the 3/2 edges. So here is the proof. So there's the Lipton-Tarjan separator theorem that tells you that in any planar graph, you can remove O of root n vertices and divide the remaining vertices into two groups of at most n/2 vertices, such that you don't have any edge between the left group and the right group. So this is a separator, and we really want at most n/2 here and at most n/2 there. And you can use this Lipton-Targen separator theorem to build a universal graph inductively as follows. So you're building the graph Gn that contains all n-vertex planar graphs. And how do you build Gn from smaller g's? So you take two copies of Gn², two disjoint copies on the left and on the right, and you add a complete graph on a constant times root n vertices. And you join this clique to all the vertices of the graph. So you have all possible edges between this clique and the rest of the graph. So it's the same as saying that you're taking two copies of Gn² and adding O of root n universal vertices. And now it's fairly clear that when you look at the separator, it's fairly clear how you would embed any n-vertex planar graph in your universal graph. You just embed the vertices of the separator in the clique, and you embed this part inductively in this part in this part. And since you have all possible edges, it's clear that your graph will be a subgraph of this graph. And it's not very difficult to prove that it has the right number of edges, n⁻⁵. Okay. So, and very surprisingly, there were no improvement at all on this bound in the past 40 years. And recently with Gavoille, Joret, and Morin, we were able to decrease the bound from n⁻³ to n⁻⁴ log 1. And the idea, so we reuse a lot of the things that I mentioned, the construction of the induced universal graph, but we cannot use the graph itself. It's way too dense. It wouldn't work. Instead, we do something a bit different. We reuse some of the ideas. And so for instance, the idea, so we use the product structure theorem, we use binary search trees, but in the induced universal case, binary search trees were able to, and we used this kind of transition codes to have labels that were not too big. Here we are going to use the transition codes in a different way. So the transition codes, these are small codes that tell you where i+1 could be, or where yourself could be in the next layer. So we are going to use that in the universal graph by saying, okay, let's take all possible transition codes on these many bits, and for each of them, I know where i+1 would be, or me in the next layer. But in the universal graph, we're going to add edges to each of these possible locations. So we are going to add an edge between I and all possible locations of i+1. And we are going to add an edge between I and all possible locations of I in the next layer. And we know, because the transition codes are small, that there are only a few possibilities of where the location could be. And we put edges in all of this. And since there are only few possibilities, we add few edges. And this is how we get a universal graph with n⁻⁴ log 1 edges. So
oh no, is this happening again?
So I was saying that very nice properties satisfy this product structure theorem, and they all satisfy our results immediately. But general proper minor closed classes don't satisfy this structure theorem. And for them, the best known bound remains 2 log n for the adjacency living scheme. So n² for the size of an induced universal graph, and n⁻³ for the number of edges in a universal graph. Because proper minor closed classes, they also satisfy Lipton-Targen theorem. So you can do the Bye-bye et al. Construction, but what we did doesn't work. So in general, it remains a very interesting problem to go way beyond planar graphs. to any proper minor closed class. And let me conclude with a related question. It's called the implicit graph conjecture. It's a conjecture of Canaan, Naur, and Rudich. So the conjecture says that any hereditary class, class is hereditary if whenever you remove vertices, you remain in the class. If the class doesn't contain too many graphs on n-vertices, so at most 2 to the O of n log n, this is the case for interval graphs, for instance, then there is an adjacency labeling scheme with labels of size at most O of log n. And actually, it's an if and only if, because if you have such an adjacency labeling scheme, then you don't have too many graphs in your class. And well, this is not completely related, but this is a very nice conjecture, and it's wide open. Actually, it's very hard. It's too general somehow. So yes, so I'm done. Thank you.
Thank you very much. Let us all thank the speaker. Are there any questions or comments?
I've got a couple. Was first of all, very nice talk, and I was impressed that you were able to improve that last result by that much over such a celebrated list of authors. I have just 2 questions. They might be easy. One is going back for a moment to induced universal graphs. What is the bound for the class of all graphs on n-vertices? Okay,
this is a very good question. So for the class of all graphs, we can prove n over 2. I mean, it's known that n over 2 is the right bound, and it's actually extremely hard to do precisely n over 2. So
oh, wait, I'm confused.
Yes. So sorry, I'm talking about. Okay, so I'm talking about the adjacency labeling scheme. So you have to make 2 to the n over 2. Sorry.
Aha.
Okay. So for adjacency labeling schemes, you can make n over 2.
2 to the n over 2. That makes sense. Yes.
Yes, exactly.
Yeah.
So for dense graph classes, there is a very natural lower bounds that comes from counting. So let me just go one slide after the conclusion, because it's a very perfect question.
You were prepared for this question.
So actually, so if you have an adjacency labeling scheme with labels of size at most f of n, then each graph in your class on n vertices is described by these labels. And you have n times f of n bits, because each label has f of n bits. So each graph is described by n times f of n bits. So you can't have too many graphs on n vertices. You have at most 2 to the n times f of n. So it means that a graph with an adjacency labeling scheme cannot have too many vertices. And if you put it the other way around, every adjacency labeling scheme needs at least 1 over n times log of the number of graphs in the family. So if you look at the family of all graphs, this would make n over 2, because there are n to the n square over 2 subgraphs. So you need at least n over 2, and you can do that with n over 2. And this was proved. I mean, it was known for a long time with the lower order term, but it was proved by Alon a couple of years ago that you can really do that.
Okay.
Also for bipartite graphs, you can do n over 4.
Excellent. Okay, so the other thing I wanted to ask was this. So in your original use of the n-dimensional hypercube for trees, you actually get something a little stronger there than an induced graph. You get an isometric universal graph.
Yeah, and also you can get the, sorry.
Yeah, there are actually applications for such a thing. Do you know any more about that for trees, for example, or for other classes?
No, I don't know much about isometric embedding, and also it's a good question. And also in the construction, I was not using the edges in the right hand copy of the n-1 dimensional hypercube. So if you just remove these edges, what you get is actually a tree that contains all trees. So it's not only the hypercube, but you get in fact a tree.
Right, right, right.
And,
Yes,
and,
do that,
and
which of course
this
would be isometric.
Yeah,
yeah,
exactly. And this is, and there's some research on universal graphs that also are in the same family as the graphs themselves. And you could also ask whether you can find a planar graph that contains all planar graphs. But this really changes everything, and all the techniques like adjacency labeling, they don't work for that at all. You need probably to reinvent things. But yeah, I don't know much about asking for some isometric embedding rather than just an embedding.
I can tell you that for the class of all graphs on n vertices, you can get an isometric universal graph with 2 to the 3 n vertices. Sorry, with with 3 to the n vertices. So it doesn't cost that much more than 2 to the n over 2 for induced.
And how does the construction work?
That's you can do that using the 0, 1 star embeddings.
Okay.
If you, I'll send you the reference.
Yes, I would be very happy. Thank you.
Okay, we'll do. Thanks again for a great talk.
Thank you.
Are there any other questions?
Can you hear me?
Yes.
I'd like to ask, I'm under the impression that the labeling scheme that you are describing can be adapted to a dynamic setting where the graph remains planar, but edges and vertices appear or are deleted over time.
Okay, so the problem is that, so we use the structure theorem, the product structure theorem, and the way we construct these binary search trees is very sequential. So we build it layer after layer. We start with the first row, and then we make some modification to get the second row and the third row. This is purely sequential. And if the vertices come row after row, I think we can do that. But otherwise, I think purely dynamic setting, I don't see at all how we could do that. We really, there's something completely sequential about the way we construct trees.
But if you would restrict your family of graphs to graphs of tree with 8, and then I would think of the path as time, then that would work, right?
Yes. Yeah, I would have to think how to build a binary search tree in a completely dynamic way in each row. That might it might be possible to do that. Yeah, if the vertices arrive row by row, yes, it might be possible. I think it might be possible, but it might. I mean, it might be a bit far-fetched in the dynamic graph community, I don't know. But yeah, I think it might be possible this way, but it's quite specific in a sense.
Oh yeah, I have a second question. If I understand correctly, the little O of log n is something like O of log n?
No, it's a bit more than that. It's 2 to the
It's
square root
bigger?
of log n, something like this.
Can you reduce this quantity if the degree is, say, bounded by 4?
You mean if you look at planar graphs of degree at most 4?
Yeah, like in Layton's work.
Okay, I haven't thought of we haven't really thought of planar graphs of bounded degree. right now, this lower order terms comes from our rebalancing strategy. So that the way we do rebalancing, we do it layer by layer somehow, and we gain something, but we lose something, and the threshold is really at this square root 2 to the square root of log n. And maybe it might be the case that if the degree is extremely small, we might be safer in the rebalancing strategy, and we might be able to get the lower order term much smaller. But it's not completely clear to me at the moment what bounded degree would imply. I think it's not clear at all, but I think it's a very good question.
I have a third question, which is
Sure,
about the structure theorem. If I understand correctly, then you could define a hierarchy over planar graphs depending on the length of the path in the product. Easy to determine what is the minimum length of the path in a decomposition would be given a planar graph.
So you would fix the tree widths of the rows, and you would ask to minimize the size of the path. Yes.
Yeah, the length of the path, right?
I don't. Yeah. Given the proof is some induction that use some topological argument, which is very simple, but you go inside some. So you fix the outer face of what you're looking at, and you're really going inside. And I don't see many ways to avoid that. Or maybe, yeah. Yeah. Yeah, there might be something to do. I don't see how at the moment, but can you elaborate on why the path would the length of the path would matter somehow in applications? On the tip of my head, I don't see how having a very long p or very small p would be different. There might be a problem with having a very small p, because then you would have bounded tree widths. So yeah, so let me tell you that. So if the rows have tree widths at most h, or tree widths at most t, then any k consecutive rows have tree widths at most k times t. So there's that. Yeah,
this is why I was. Yeah, this is why I was referring to this as a type of a hierarchy over planar graphs.
Exactly. So if your graph has tree widths at most has tree widths square root of n, then you know that you will never be able to avoid the square root of n divided by 8 rows, for instance. I mean, you know that you won't be able to do better than that. Okay, because any k consecutive row has small tree widths. So somehow it tells you that if the tree width is quite large, and can be as large as square root of n, then you will never be able to embed your planar graph in such a small height grid.
Yeah, thank you.
No, thank you for your questions.
Are there any other questions? I have a small questions actually. It's also about the lower order terms. You might have said this, but I don't remember. Do we conjecture now that the bound for, say, planar graphs, for, say, induced universal graphs or planar graphs might actually be linear?
Yeah, there's no lower bound contradicting that. Yeah, it could be linear, really. And it's terrible, but lower bounds are very bad in this regime. So here you have some counting lower bound, but in the regime of planar graph, there's nothing more than log n plus some very small constant for the scheme, or very small constant times n for the induced universal graph. And it's very likely that you can achieve that. The history for dense graphs is that you can really achieve the exactly this counting bound.
Mhm.
So yeah, even without the lower order terms.
Thank you. Yeah, any more questions? Okay, if there are no more questions, then let us thank Louis again.
So thank you very much for your attention.
And the next week's talk will be at the usual time at 3:45, and the speaker will be Theo Molla from University of South Florida.